Hello and welcome back. So now we're going to delve into chapter 6, where we start to look at the idea of data structures, right? These are absolutely fundamental. As we'd spoken before, we mentioned that Nicholas Wirth, the inventor of Pascal, actually wrote a book called Data Structures plus Algorithms Equal Programs or Computational Solutions, thus indicating the centrality and importance of data structures and how your choice of data structure inherently influences your choice of potential algorithms and the reverse as well. So let's just step back a bit. The story so far is that we found that data was made up of the structured raw facts or values that we actually observe from the physical world. And the way that we organize this data has a significant impact on how effectively it can be used. And the types of values that are represented by the data, those structured values that we have, right, the structured raw facts, also determine the various operations that are defined on it. So, for example, if you have numeric data types, then you can do certain arithmetical or mathematical operations on them. And if you have a string data type, then you can only do textual or string operations on them. We also looked at this idea of abstraction, which was the idea of ignoring details or hiding certain details about the system that we deem to be unessential to the particular problem that we're trying to solve. And that helps us model or represent the problem in a simpler way that we can then solve, hopefully. So we're going to formalize this approach for different data representations and different data structures. To do so, let's step back and start to look at a simpler idea. And we're going to look at this idea of, let me just put that down a little bit over there so that's visible. And we're going to look at the idea of nails and screws that you might be more familiar with, right? And we'll see that it's a very familiar idea, that the idea that different types of data hold different kinds of values, and so by dint of that have different kinds of operations that you can associate with them. Hopefully this idea of looking at nails and screws will bring that to the fore. So we can distinguish between two types of fasteners that you might have. One of the fasteners might be nails and the others might be screws. And we can distinguish them based on their characteristics. For example, we might say that a nail has a thin, flat head with no slots in it, but that a Phillips screw, for example, has an X slotted in its head, right? So these are the different kinds of values that the characteristics of the head of these fasteners might have. And then because of the different kinds of characteristics that they have, the different kind of head that they have, you can have different operations that you can do on them. The operations, the kinds of things that you can do to or with them. So the operation that you can do to a box nail would be you can hammer it, right? You can just basically, it's got a flat head, so you can just hit that sucker. But what you can do with a Phillips screw is use a Phillips screwdriver and use the benefit of an inclined plane to sort of have it penetrate surfaces differently than you might using just an ordinary box nail. So what you might do is start off by looking at these different kinds of fasteners and try to abstract out the essential elements of all fasteners that you might have. You might say, okay, they have a certain value for the head characteristic. For example, you might ask, is it flat or is it slotted? Then you might have certain common operations. They can both be inserted using some kind of driving implement. There are different driving implements. For the Phillips screw, you need a Phillips screwdriver, and for the box nail, you need a hammer. But the operation is that, you're kind of using some driving implement to insert both of them. So you can specify an abstract representation of it, what we might call as abstract fastener type, which talks about the commonalities of the characteristics and the operations on both of these or all of these different kinds of fasteners that we have. We might represent this abstract fastener type using some kind of a blueprint or an outline. And so that outline is represented here where we might use, just a little flowchart type symbol. This happens to be in a language called Unified Modeling Language, and we use UML, Unified Modeling Language, to represent these kinds of abstract structures and to encapsulate them in a very nice compact form. And so we can see that this abstract fastener type has a name, it has certain characteristics, and it has certain behaviors. For fasteners, the characteristic is that the head that it has a head. Now, the kind of head that it has, the specific kind of fastener, we don't provide any details of that. We don't say if it's a flat head or if it's a slotted head. We just say that a fastener, so if you're trying to describe fastener to someone that doesn't know them, what's a fastener, right? You might say, oh, there are different kinds. There's nails, there's screws. All of these things are fasteners. I say, what do you mean by fastener? Well, we mean a fastener is something that has a head of some sort, right? That's one of the characteristics that we happen to define for it. And then what do you do with a fastener? What do you do with a nail and a screw and all of these other things? Well, you're able to drive them in somewhere. That's the behavior that the fastener has. So if we were to abstract it out and simplify and look at the commonalities across all these different kinds of fasteners, what do they have in common? Can we describe them somehow together? Can we classify them together in some way? What we might say is, yes, we can, by defining this abstract fastener type. And it turns out this idea of an abstract data type is just like the abstract fastener type. And abstract data types delineate the characteristics and operations for all kinds of data, not just for fasteners, right? And so this abstract data type denotes the kinds of characteristics a certain data structure can have, and also the kinds of operations that it can do or have done on it. The abstract data types show what they do, this is the important part, but not the details of how they do it. This is why they're abstract. We're ignoring those details that we deem to be unessential in this case. And for this reason, the abstract data types are sometimes also called the specification or the interface for the data type as well. And so you can see that if we were to look at these certain data types that we have, like float and int, you can see that they have certain characteristics and operations in common, and that they do certain things and that they store certain things as well. A float, for example, stores a real number. It can only return a decimal number using the plus operator. An integer stores an integer value, and it can only return a whole number. And it also uses the plus operator to do addition for it as well. So what are the advantages of defining these kinds of abstract data types? Well, one of the advantages of these abstract data types is that they make our computational solutions simpler and easier to understand or modify because they get rid of and omit some of the details that we deem to be unessential of how the operations will be implemented. They get all of those details out of the way. So that means if someone's trying to use this abstract data type, they don't need to know exactly how some operation is implemented. They just know that it has that operation and they can use the data structure to do that operation then. So an example is that all fasteners have the ability to drive in. They have the drive-in operation, but the abstract fastener type doesn't specify that they should all only use hammers. It depends on the implement that's going to go with it. So the ADTs give us the flexibility to structure the data in memory in the way that's going to be optimal for that specific data type without forcing all data types that are of a similar kind to follow the same approach. So for example, all fasteners have a head value, but the abstract fastener type doesn't dictate that they have to have the same head value for all fasteners. One kind of fastener, the nail, might implement it as a flathead. Another kind of fastener, the Phillips screw, might implement it as an X slotted head, right? So the ADTs also help us support the reuse and organization of our data structures by providing the ability to generalize the use of similar data types and the ability to group tasks together. For example, we can also specify that we'll use a fastener for two tasks in some solution, and the two tasks can use different types of fasteners, but we know that both tasks are going to be fastener type tasks. That means you're going to be driving in something and you're going to be maybe holding stuff together. You're not going to be using a shovel to dig up dirt, right? You know it's going to be a fastener type task. You just don't know the exact detail of that task. And we'll see how this sort of seeming ambiguity can be helpful to us later on when we start to talk about different data structures. So often in the terminology, it gets confusing between data types and abstract data types and data structures. It's all thrown about. But the data type is you can think of that as the logical expression that doesn't depend on any language at all of a certain type. That's the collection of values as well as the operations that are permitted on that type of data. An abstract data type is also a logical specification of a data type, but it's in some particular language, but it does not include any of the implementation details. The data structure is the actual implementation of that abstract data type in that particular language for which it's defined, right? So this is sort of how these guys are related to each other. It can get confusing, but you can get a handle on that. The ADT, the abstract data type, is just the interface, right? It doesn't have any of the implementation details. So in a sense, it's a theoretical representation of the data type. The abstract data type is a logical description in some language, of course, but without the implementation details. And the data structure itself is the concrete implementation of that actual data that you have. A particular data structure gives you the concrete implementations for both the characteristics or attributes that it has, as well as the operations that it's capable of. And this idea of differentiating between the logical interface versus the physical implementation is very important. It's because it lets you examine what a system does without looking at the details of how it does it. So this idea of only examining what a system does is a form of abstraction, hence the word abstract in abstract data type. The abstraction allows us to differentiate between a logical view of the system and a physical view of the system or problem that we're dealing with. The logical perspective of the system is also what we sometimes call the interface or the logical interface in general. So for example, when you turn on your TV, you might use a remote control, and you don't need to know anything about the internals of the TV, how it works, how the image is produced, does it use rasterization, what do the circuits look like. All of those details, the circuitry and the machinery of the television, are part of the physical implementation. And the remote control in this case would be our logical interface. All it would reference is what the TV does and not the details of how it does it. And so the same thing happens with other computational data structures that you might have or computational data that you might be looking at. We've seen strings already. A string is also an example of a sequential data type in Python. Some useful sequence data structures that Python gives us other than that are things like the list and the tuple. We'll see that in a bit as well. A string, you can think of that as an ordered collection of characters or some valid symbols in a language like Python. And in Python, that's exactly what it would be. This ordered collection is called a sequence. And since a string is composed of multiple characters, it's also sometimes called a compound data type. And so this is different from data types like int, right, which is just a simple data type since all it does is hold a single value. A string holds multiple values in this sequence that we have, or this ordered collection that we have. And it turns out that we can access each of these individual components of a string as each of those characters or elements is assigned a unique index in that string. So for example, we might have a string like mango, M-A-N-G-O, and each of these individual characters, M, A, N, G, and O, Thank God we can go with bingo, right? Bingo. Otherwise, we'd be singing this about now. But each of these individual characters can be accessed via the index, which is basically a number that indicates the position of that character in the string. That index, we can see that here in brackets, starts at 0, as arrays and sequences are 0 indexed in both Python and Java and C and C++. This harkens back to historical reasons for doing so. But this often leads to this infamous error called the off by 1 error, in which most of us forget that the indexing begins at 0, and maybe we started thinking like the first element must be at index 1, but the first element is actually at index 0. The second element is at index 1. The third element is at index 2, and so on. And some languages, like MATLAB, for example, don't follow the zero indexed scheme, further confusing things for people, and programmers in general. But if you have this off by 1 error, you'll hopefully catch that, and we'll reduce it. And sometimes the compiler or the operating system help you out with that. You can use the index combined with what we call the subscript operator, which is indicated by 2 brackets, right? Not the braces, but the brackets, to access any element at that specific index, or in Python at the range of indices. So you can see if we've got this string called mango, we might store mango as a string in this variable called foo. We can access the first element of mango, which is the letter M, by using the name of the variable foo, which contains the string, which references the string called mango, and then the brackets, right, the subscript operator, and then within that, the index of the element that we want to access. So we might say letter is equal to foo 0. That's how we might read this line. And then we can print that letter, and we see, sure enough, it prints out the letter M. But we can also access a range of sub-elements. In this case, it goes from the beginning index 0 all the way to 1 minus the last index 3. So it'll go from index 0 to 1 to 2 and include all 3 of those characters or sub-elements, and that's what's stored in letters. So letters itself is a substring, and that substring is what we print out when we do that. Now, there's some oddities to how Python processes strings, and they make life a lot easier for us, but they also make it somewhat confusing at times, depending on what your background is and how you're coming to it. You can access any subsequence of characters in a string using that subscript operator, and so you can indicate individual elements with a single numeric index, as we saw, or a numeric range with the colon character, as we saw as well. And this is sometimes called slicing a string, since you can slice it up into different substrings. And as we said, it ranges from the lower index all the way to the upper index -1. And if you leave off one of those indices, if you leave off the first one, for example, it starts from the beginning. If you leave off the second one, it assumes you mean to go to the end. The other thing that's kind of odd about strings in Python is that they're immutable. This is actually true for all objects and values in Python. So unlike other languages like Java, you can't use the subscript operator to assign a value to it, but you can only access it. But you can use the subscript operator on a string to access any of those individual elements or range of elements that you want. And if you're accessing a range of elements, normally you'll use a for loop. And this is similar to like the enhanced for loop. Let me extend that out a little bit so it's easier to see. So here's the for loop. For each letter in foo, each letter is a local variable, and it's similar to the enhanced for loop in languages like Java, etc. It just makes processing strings and, as we'll see, lists in general a lot easier in Python. So as we'll see, it turns out that just about everything in Python is an object. And so strings are also objects. And they're objects which you can think of as being derived from an abstract data type in a way. We'll explore this idea of objects and classes in more detail later on as we get to the object-oriented programming chapter as well. But just about everything in Python is an object. Ironically, even though Java was designed to be object-oriented from the ground up, it's not as fully object-oriented as Python might be. Objects have this unique characteristic that that objects have access to both their data, like the string value that's stored in a string variable, as well as the methods or operations that you can perform on that data, right? So we can use any string method using the string object's name or identifier. It's the name of the variable that represents that object. It's usually an object reference variable, followed by the dot operator. The dot operator is our key. The dot operator is represented by a period, and it lets you access any sub-element or subcomponent or method or service that an object provides you or a class provides you. So for example, we have that same string foo. We can invoke or call or utilize the upper method of the string class by using the dot operator on the object reference variable called foo. So we can invoke the upper method on foo by using the dot operator. Similarly, and then what that'll do is it'll make all the characters uppercase, as you see. Similarly, we can invoke another method called lower by using the dot operator and doing that. There are a bunch of other methods that are also available to us for strings. Another kind of very useful way to sort of organize data is in a list, right? It's one of the most obvious and useful ways that we organize data. You use lists all the time in your everyday lives, I'm sure, to do things like construct shopping lists or to-do lists or checklists and things along those lines. A list is basically a means of structuring and accessing a collection of data. In particular, it's a way of organizing data in some kind of sequence, in some kind of linear sequence. And so the list data type or abstract data type can keep track of elements in a list. We can define this abstract data type called list and just take advantage of the features of an abstract data type to define both the characteristics and the attributes or characteristics, as well as the operations or methods that it might have, without defining any of the implementation details. The list ADT describes what kinds of values lists can hold and the operations they can have. In this case, we might call that list objects, right? So the list ADT describes the kinds of values list objects can hold and the operations that list objects can have, either done to them or done by them. So some of these are things like insert a new element, locate an existing element, delete an existing element, etc. And we can create different specific implementations or data structures of lists, like an array list, a linked list, etc., which implement that required behavior in a very different way. The different ways to implement the list ADT depends on the kinds of problems and the data structures that it'll help tackle. Python happens to do it a certain way. Python has these lists and tuples, and one of its list data types is called, nicely enough, list. Just like a string is a sequence of characters, a list is essentially a sequence of values of any type at all, including other lists or tuples. So a string would be a homogeneous data structure, and a list would be a heterogeneous data structures. But just like with strings, we can also use the subscript operator to access elements or subsequences of these lists. And unlike strings, lists are actually mutable. You can actually change the values of those elements as well. So you can use the subscript operator to both set or change the elements of a list as well. And you can, of course, still use loops to traverse or access all the elements of the list, just like you might for the string data structure that you have. We can also use built-in methods of Python like length, len, to find the length of any sequence like strings, lists, or tuples. And there are many methods that are only available to list objects that allow you to do things like append new elements to the list, extend the list with another list, and sort the elements of the list. We can do things like also use the plus operator to concatenate lists, the asterisk operator to repeat a list, For some number of times, it'll be a binary operator, and so the right operand will determine the number of times you'll do it. And we can do the same kind of slicing and dicing as we did for strings. Finally, the cousin of the list is something called a tuple, and it's just like a list, except when you declare it, you use parentheses rather than brackets. And the other major difference is that it's immutable once you've created it. So it's closer to the string in that way. But tuples are also objects that are comparable, which means that we can sort lists of tuples as well. And they're also hashable, which is helpful when we meet other advanced data types like dictionaries, which we'll see later on. So until then, we'll see you next time. Bye-bye.